In this video, we'll learn the derivatives of our 6 trig functions. Now, I could just give you a list and tell you to memorize the formulas, but I think it's much more interesting to discover what those derivatives are. We're going to do that in 2 different ways, starting with a couple graphs, and then we'll actually look at the rest of the trig function derivatives by using our quotient rule. So join me here in this first example. We're going to find the derivative of the sine function. I went ahead and drew one fundamental period of sine, and mine is kind of lumpy, so I'm hoping you can come up with a nicer, smoother curve. But we'll look at the behavior of that function and translate it to the behavior of the derivative, and then come up with what the derivative function looks like. Reading our graph from left to right, we see that starting out right at negative pi, we have a decrease, and then it has an increase in the middle, and ends that fundamental period with a decrease. And at the min and max here, they occur at negative pi halves and pi halves. We know that because trig functions are very symmetric. So halfway between 0 and pi and 0 and negative pi will be those max and mins. And we also know that at those max and mins, the function goes exactly horizontal there, so we call those horizontal tangents. So I took all that information about f of x and translated it to what we know about f prime of x based on that. So we have a graph that's going to be negative below, positive above, and then negative below, and have x-intercepts at those negative pi halves and pi halves values. So I started by placing my x-intercepts at negative pi halves and pi halves. I made sure that my graph was below, outside those two intercepts, and above in between. And I happen to know that the derivative of a trig function is also a trig function, so I made these outside curves nice and flatten out. And I hope you can recognize what we're looking at. The derivative of sine is the cosine graph. So now that we know that the derivative of the sine function is the cosine function, let's go ahead and use that same investigation to find the derivative of the cosine function. We know what the graph looks like. We just saw it. We're graphing it again from negative pi to pi just to get one fundamental period. That'll be enough information to figure out what's going on. And we'll take its behavior and analyze it using a sine chart. The cosine graph has less changes in behavior on this fundamental period, so let's take a look. It is increasing, followed by a decrease. It changes at exactly x equals 0, so that's where we have our horizontal tangent, and that'll correspond to an x-intercept at 0 on our derivative graph. One thing that you might not notice right away is that since the cosine function flattens out here on both ends, those are actually going to be horizontal tangents as well. So let's go ahead and add those into our sine chart because it'll help us draw our derivative graph. I decided to make those horizontal tangents a little easier to find on the graph in case you weren't spotting those on your own. So in our sine chart, we now have a horizontal tangent at negative pi, 0, and positive pi. So those translate right over to x-intercepts on our derivative graph. And so to put the behavior of above and below, and knowing again it's a trig function, it's going to be nice and curvy between those intercepts. We have this graph. I hope you recognize it. It looks like the sine graph, but it's opposite. So the derivative of cosine we have discovered is the negative sine x. So while I think it's really neat to see those two derivatives using graph analysis, I think it would be a lot to do 6 graphs. So let's go ahead and use another skill that we've learned and give us a chance to practice, and that's the quotient rule. So we're going to take the derivative of the tangent function using the quotient rule and figure out its derivative. And you might be thinking, well, tangent doesn't look like a quotient, but we know that tangent is actually the quotient of sine and cosine. So let's take a look at that. I jumped right into the problem and forgot to explain this d over dx is our notation for derivative. It's our Leibniz notation. Since we don't see it that often, I just wanted to make sure you were comfortable with what that's asking us to do, and that is to find the derivative of tangent of x. So we decided we're going to find the derivative of tangent of x by using sine over cosine definition of tangent. And let's go ahead and apply the quotient rule using sine as our high and cosine as our low function. I've set up our template for the quotient rule. I copied down the functions that we know, so we know that low is cosine. Our d high is going to be the derivative of our sine function, and we just learned that that is the cosine function. Quotient is minus. We copy our high, which is sine, and then our d low is the derivative of cosine, and we just discovered that is the negative sine of x. All over quotient rule says low goes in the denominator, so I have cosine x times itself. So when I start multiplying, I see I have a cosine times itself. That's going to give me cosine squared of x. Then I have a negative sine times another negative sine, so I need to make sure to make that a positive sine squared of x. And on the bottom, we have another cosine squared of x. I'm hoping the numerator looks really familiar to you. It's the most important trig identity. Do you know it? I know you did. It was 1, and we still have this cosine squared x on the bottom, or in the denominator. So we can go one more step, because I know you don't want this trig fun to end. So we know that the 1 over cosine is actually defined as secant. We make sure that our secant is squared because our cosine is squared. So, long story short, the derivative of tangent is secant squared x. To find the derivative of cotangent, we would approach it in very much the same way, knowing now that cotangent is cosine over sine. And if you go ahead and do this quotient rule and simplify using that trig identity, you are going to get negative cosecant squared of x. So I challenge you to try that one off to the side and see if you can get it. We're still going to use the quotient rule to find the derivative of the cosecant function, because we know that the cosecant is defined as 1 over sine. So when we set up our quotient rule, our high function is just that constant 1, our low function is sine x. So when we set up our quotient rule, we get low, which is sine x, our d high of the high function, which is just 1, since it's a constant, will be 0, minus our high function of 1 times the derivative of the low, sine x. Derivative is cosine x, all over low, which is sine x times itself. So when we start simplifying, we get that 0 times sine x, which totally cancels out that term. So we're left with a negative 1 times cosine x. So we have negative cosine x over sine squared x, which is a perfectly correct answer. But if you had this on, let's say, a multiple choice question, they'd want you to simplify a little more trig. So let me show you how to do that. It might have saved us a little time if we had realized to actually keep these terms separate would help us simplify the trig a little bit better. So the negative 1 over sine x gives us a negative cosecant x times cosine over sine is cotangent x. So the derivative of cosecant is negative cosecant cotangent. Finding the derivative of secant is very much like the derivative of cosecant in that we're still using a quotient rule. We have a 1 over cosine x this time, and your final result will be secant x tangent x for the derivative of secant x. So if you have a moment, go ahead and try that with the quotient rule, and I think you'll get it. So moving forward, we are going to have these 6 trig derivatives memorized, which is not easy, but it's definitely manageable. A lot of people have come up with different tricks and memory devices to help us remember these. One that I had students point out to me recently is that the derivative of all the trig functions that start with a c turn out to be negative. I hadn't noticed that myself. So cosine, cotangent, and cosecant all have negative derivatives. And there's different things you can find online about how to memorize these. I'm going to give you a very old-fashioned tool when you get to class, which is a set of flashcards. I think those still work. But if you think of any tricks or hear any or see any, I'd love for you to share them with me so I can pass them on. We'll go ahead and save the examples for class. See you then.